In this video we will learn how to forecast a time series using ARDL approach to Cointegration in microfit. Now I have some data here to demonstrate the process. I would like to forecast industrial production using experts and oil prices, real oil prices. So this is a data set I will use to pick up the three main variables that I need. Now I have created first difference variables here. All of the variables are first difference. I mean my variables are first difference here, which we will be used in the process, in the model estimation process. Now I'll go to single estimation menu, single equation menu, and from there I'll go to univariate and choose linear regression menu. Out of these 9 options I'll go to OLS, ordinary least squares. Now this is the OLS menu. Here I'll have to enter a linear equation which I will use to find out whether there is a common relationship or co-movements, how to say this, an association between the three variables. So in other words, I'm trying to find out if my variables are co-integrated or not. To do that, I will type the I will use a bounds testing approach. In ARDL Cointegration method, you'll have to do bounds tests using an f-stats and comparing the f-stat to the critical values populated by Pesaran and Pesaran in 1997. Now the equation looks like this here. Now, unlike the e-views, by the way, unlike the e-views procedure in microfit, we will use variable addition test rather than volt test, because volt statistics in microfit, volt statistic doesn't give us. Volt test doesn't give us f statistic. So this actually gives us a chi-square statistic. So we will use now variable addition test option in microfit. Now what I want to do is I want to estimate an ARDL equation, which I will type and explain in a few minutes. So I would like my variable dependent variable to be LNIP. Ln is log, natural log of IP, industrial production. Now I want it to be first difference. DLNIP is the first difference of industrial production variable. Now I'll put my input. Input is constant. In e-views we say it's C. Now I want the first 12 lags of LNIP. So DLNIP, sorry, first difference LNIP. Curly brackets from first leg to 12th leg. Now I will now start typing my independent variables. They are D, Ln, ROP. Now ROP is real oil price, Ln is a log, so first difference of logarithm of oil price, first to 12. Then D, Ln, X, experts, and first to 12. Now you might be wondering why 12? Why 12 lags? This is a monthly data set, so I'm using 12, and in a year there are 12 months. But if you're using quarterly, recommendation is 4 lags, because 4 quarters in 1 year. And if you're using annual data, it's up to 2 lags or 4 lags. Then it's most desirable to choose the 2 lags. But there is no theoretical underpinning as well to choose 12 lags for monthly. But it's just, I think it is more. It will capture more variation in the data that could happen in 1 year if I choose 12 months, because mine is a higher frequency data. It's better to have the 12 months. You could choose 6, you could choose 12. There is no sort of clear-cut theoretical underpinning for that. You can study your variables and see the pattern and choose, depending on that, choose the variables, or you can choose the lag length based on archaic information criterion and all this, but you need to run the model for that and then check the archaic information criterion and choose from there. But to save time, I think I'll go with 12 months rather than trying to do archaic information criterion. Now I will have to now choose the sample period here. I will have my starting date of my sample 1999 month 1 to 2011 month 6, but I will hold back last 6 months of my 2011. So I'm estimating the ARDL model until 2011 month 6, but I'm holding back the remaining 6 months because I want to forecast the remaining 6 months and check the performance of forecast using ARDL approach to Cointegration. So I'll hold back this. So my holdback period is the next 6 months, and these are the list of variables, but you can ignore them. Now start date is 1999 January, and end period of the sample is 2011 June. And here is my equation. This is, if you look at this, it's actually partial equation. The ARDL equation looks like this basically: ln IP. Now I have to enter the level variables here, ln x, the same variables. I have 3 variables. ln ROP. This is my ARDL, full ARDL equation here. This is my ARDL model. However, what I say, as I do leave, I will delete this because now I will estimate the model in this form, and then I will add the level variables later and check if the added variables are jointly significant or not. If yes, then I have the co-integrating relationship among them. So let's now start estimating the model. Start it. Now ignore this. Okay, and here is the model. At this stage you can ignore all the diagnostic test results here. Now all these, okay, 12 flags, 12 flags, okay, everything is 12 flag here. Alright, I'll close it and click number 2, move to hypothesis testing menu, and from this hypothesis testing menu go to option variable addition test and press OK. Now these are the variables that my model estimated, sorry, the coefficients my model estimated. Now I want to add these 3 variables to the list already estimated and see if the addition yields me a significant, sorry, in other words, what I'm trying to say is that in this test the hypothesis is that they are jointly equal to 0. In other words, if I reject this hypothesis, then there is no correlation, sorry, there is no co-integration among these 3 variables. But if I don't reject, fail to reject the hypothesis, then there is no co-integration. But if I don't reject, sorry, if I reject the hypothesis, not hypothesis, then obviously we find correlation among, sorry, co-integration among them. Sorry, my brain is malfunctioning for some reason. Now I'll press OK. So I'm adding these 3 variables together to the estimated model, and I'll see if they're jointly significant or jointly needed in the equation or not. If it's needed, then there is a co-integration. So in other words, they need to be there. If they are sort of repelled by the estimated model, or if they refuse to enter into model, then obviously there is no co-integration. So well, let's see, I added these values and I'll press OK. Now we ignore the first model and we go to the bottom of the model, and this is what we're looking at: F statistic and 3 variables. This is the degrees of freedom, and here it is, 7.57 and 0% probability value. So we will reject the hypothesis, null hypothesis, that they are not needed. They are actually needed in the they are not equal to 0. Basically they are required, they need to be in the model. So that's the result here, and 0.5762 is something we need here. This is the F statistic which we will compare against the critical values from the pre-populated bounce testing critical table. Let me bring it here. Sorry. So these are the critical values for bounce testing, pre-populated by Pesaran and Pesaran, and you can find them in page 478 if you open. So this is the book basically. This is a microfit book. They give you when you buy microfit software, or you can find them in your libraries usually, or you can go to the Pesaran 1996, I think. It's an article about long run estimation of long run cointegration, something like that. I couldn't remember it now off the top of my head. However, here is the table that we're looking at. We are looking at the middle table. There are three tables. The first one is when you don't have any intercept, any trend in your model. Second one is when you have only intercept but no trend, and the third one is when you have both. But in my model, if you remember, if I move it down, I have input, so no trend, but I have constant basically C. Now I'm looking at 95% level, so my K is number of regressors, the independent variables. I have two of them. I have three variables, but two of them is independent variables. So this is the one. So I go along this line and I look at this value. This is the lower critical value, which is 3.793. Now my F stat is 7.57, which is greater than this, but also greater than 4.85. So above the upper bound. My F stat lies above the upper bound at 95%, and even above the upper bound at 99% level as well. So that means there is a strong evidence of cointegration among my variables, among my three variables. So sometimes, I should say, sometimes we get 1.5 here and very significant value. That also tells you that the three variables need to be there. However, if the critical value is not greater than the upper bound, I1 upper bound, then there is no cointegration. So we shouldn't look at the probability value, and if it's significant, then if it's less than 0.05, then say there is a cointegration. In fact, there is no cointegration. Mightn't be any cointegration. This is the value you should look at. Sorry, I might have told you something different earlier, but in fact we will ignore this. This is the significance test for addition, but we will look at this only. So this has to be obviously significant. Then you take this value and compare it against that. Now we have a strong evidence that there is a what you call this, cointegration among the variables, because our F stat lies above the upper critical bound value of the table. I mean critical values populated by the Pesaran et al. 1996. I think they did it for the first time. Now I will close this because we don't need it now. We just got an evidence that there is a cointegration, so I can now estimate estimate the long run and short run effects or interactions among these variables. Now to do that, I will go to now univariate ARDL approach to cointegration. From there in there I keep the starting and end period as it is, 12 months I leave it, and I will delete all this. I don't need it. I will now enter another set of model ln-IP, ln-X, ln-ROP, and now here I will put AND before entering my deterministic variables. They are input, which is constant, and trend. You can also enter any dummies, but you need to first specify them in the data. You need to have the dummies first. So you create them in the process here, and then put them here, and then put them there. So you can put your dummies after the term end. Now 12 months lag and all this entered. ARDL approach to cointegration, and here is my model. Now I'll start it. Usually when you have a lot of lags and a lot of variables, the software will take longer to estimate it, but it's good that it didn't this time. Now here it is the model selection criterion menu. You can select based on R bars, adjusted R square, archaic information, or Schwarz-Bayesian or Han-Quinn. I prefer Schwarz-Bayesian criterion. I think Pissaran and Pissaran themselves also recommended this in one of their articles, so click that. Okay. Now we will see the estimates of ARDL regression. This is the main ARDL regression, and interestingly everything is significant. And good thing is I have negative correct sign for ln ROP, and interestingly negative also for X as well. So in the first month, first period, there's a contemporaneous, how do you call it, current periods effect is positive. However, then effects of 2 period ahead and 2 period earlier effect and 3 period, I would say 2 period, because this is the current one, this is the last period, and this is the period before last period. So these are negative effects. That's interesting finding, but we will check. These are not very interesting for us now. We will be looking at long run and short run effects rather than these. So, but it's good that you have negative significant values. But now let's check the overall model fit. Now 97% of variation in industrial production is explained by the model. That's a good thing, and that's significant. That's even better. And then we have Durbin-Watson statistic, which is around 2, which looks good, because around 2 means no serial correlation, first order serial correlation. Now higher order serial correlation also failed to reject that there is no serial correlation, so that's good. And functional form is correct, and heteroscedasticity, so no variation, but normality we didn't pass that, but not a necessary condition now for a good model. So all the tests passed, literally I would say virtually we passed all the tests except for normality, residual normality test. We can ignore that now, so close it. Now cancel, and we go to this long run coefficients or long run model. Now long run model is also very significant, and the good thing is ROP is negative. In other words, in the long run oil price changes affect the industrial production or manufacturing, in other words, negatively, which is possible and according to the theory, because high oil prices usually reduce the production in the long run. So if oil price is £10 today, you produce a lot of things, but after 2 months oil price is £100, let's say, and then within 2 months of time you don't produce a lot because people don't buy at a high price, because you can't put it at a low price if you're paying a very high price for an oil. So you're paying now more for an oil, or barrel of oil this time compared to last time, so you have to price higher, and then higher prices means people stop buying, or they might find it hard to buy, and it also pushes the inflation up as a result. Now high exports increase the industrial production. That's right, because the more you export, the more you produce, obviously. Especially good for those countries who are export oriented, or whose economy is driven by exports, such as China, Brazil, India and Russia. Now ignore the input, this is high as well, significant as well, but we will ignore that. Close, and we go back to cancel and display error correction model. Now we will go to short run effects, so they will discuss the long run effects. So in the long run they are significant, the variables significantly affect the production, or determine the production significantly. Now interestingly and very importantly, we have error correction turn significant, and it's negative, which means it's stable, and also the value here is small though, however, so it's a slow adjustment. In other words, 8.1% is a slow speed of adjustment. Basically, the negative sign means Y lies, in other words, IP lies above the equilibrium and comes back to the equilibrium in the next period, if this is negative. But if you have positive sign here and significant coefficient, then Y lies below the equilibrium, so and then adjusts back to equilibrium late in the next period. In other words, last period's deviation from the equilibrium adjusts at a speed of 8.11%. So that's how you can explain this value here. So the higher the better, obviously, and in absolute value the higher. So at the moment it's 8%, ignoring the minus sign. So if it's 50%, 70%, that's even better, because that's a quick speed. So the economy is robust. In other words, if there is a deviation, let's say things are moving properly, like three things are moving, these exports, imports and oil price are moving together higher and increasing together, but suddenly one of them deviates from the equilibrium, the distance between them actually changes, and then IP, let's say IP value comes back to it at a speed of 8%. So it comes back to the normal speed as it is before. So just to adjust, if you think about a race, if three cars are racing and one of them deviates when it comes to turning point, when it deviates slightly, but if you look at them in the long run, it just comes back to normal again. So the same thing here, in the short run it deviates by some value, but in the long run it comes back to normal at a speed of 8.11%. So it's like if you look at the bike racing as well, the same thing. The bicycles move together until the finish point, but in the meantime, in the long run, they move together for a while. So one or two of them actually deviate when they turn around and turn right, turn left, but they come back again to normal things. So if you imagine the same thing here, so economic variables sort of deviate and depart from each other in the short run, but come back to normal in the long run. So normal sort of speed, normal sort of pattern in the long run. So this is how it is. But if you have let's say non-significant value, then they don't cointegrate. They might be moving around as they wish, but this is significant, so they do go together. Now in the short run, positive impact, that's good, from exports. So lagged exports again in the short run, increases in exports, increase in manufacturing. And a good thing is oil price in the short run, increases in oil prices reduce the industrial production by 5%, almost 5%. You can ignore the input. Now interestingly, we have only got 50%, around 50% of explanation, but it's significant, so that's not bad. Okay, and now these are the short run effects. Now basically short run effects adjust and then move the variables to the equilibrium in the long run, basically. Now after this, I'd like to go to forecast menu, so can't close it. Now compute forecast from ARDL model. Okay, now it says initial observation in the forecast period is 2011 M7, final observation is the end of the year, so it's M12. And which one would I want to forecast? I want to forecast all 6 months, so I press OK and select required option and press return. So I have to choose the variable I wish to forecast. As you know, I have lnip as my dependent variable. That's what I want to forecast, giving condition to these variables, conditional to these variables. So okay. Now do I want to forecast change or lnip or levels? I want levels. Press OK. Now I want to display the forecast errors and forecasts. Now these are actual values which I held back earlier. These are actual values, and these are the predicted values by using the past data. If you look at them, it's very accurate. There are slight deviations, but this is a crude measure, so I would like to look at this here, the accuracy check. So I want to look at root mean squared errors. Now 3% error in the estimation period, in the sample period, but 2.5% error at forecast period. So this is a very small marginal error, so that means it's an accurate forecast, but it's good to have something else to compare it. So you could use, let's say, Garch, Arch, or T-Garch, or some other method. Maybe you use just a linear regression to forecast Y and then compare it against the performance of ARDL model as well. So at the moment on its own it's good, but this value really is for comparing it against some other values, some other sort of models, methods of forecasting. So at the moment it's good. So close it. Now I want to plot the forecasts. So second option, okay, and I want to forecast it for the whole period, wave available. Now that's good, actually. This is very close, and I don't know if I can zoom it a bit. Let me try. No, I can't zoom it. So now this is the actual value, and the lightly colored is the forecast value. So in fact they match, they fit very well. The forecast values are fitting very well, and then even out of sample fits very well. So it's 2.5% error here, so not a bad performance. This is the demonstration of how to forecast time series using ARDL approach to cointegration, and I think this is a good one, but I haven't tried it other models to forecast. I think there are time series approaches as well, time series techniques to do this. This is more like a regression approach here, ARDL approach, but you can use the time series approaches like Garch, Arch, T-Garch, P-Garch, and all other methods. Now with this I demonstrated how to estimate or how to forecast time series or economic variables using ARDL approach to cointegration. Hopefully you will leave feedback on my channel, so under this video, so that any mistakes I made, I might have talked about things that aren't related to this, or maybe some comments were mistaken. So bring them forward and raise them, and then come back in your comments, please, and then I will improve the videos in the future. Okay, and see you later then.